Hi, welcome to Module 1, Lecture 2. So this is going to pertain to, if you go to the Module 1, Lecture 2, we have the lecture slides here, and then we also have the R code, and I'll be uploading this video afterwards as well. So what we'll do today instead, I think it would be better just to stick in the PowerPoint presentation, and then we can actually walk into the R code again and walk through everything. I think we did that in reverse last time. I apologize for that. All right, so today we're going to be talking about random variables. So random variables. So consider a coin flip. Let's say we flip coins. And remember, right, last class we talked about don't be afraid of X's and C's and Y's. Those are just variables. Those are values. You could have xi, that's the ith value here. So consider a random variable X that takes a value 1 if you flip a coin flip, and it's heads, and 0 otherwise. So it's kind of like an indicator function, right? It hits a 1 if there's a heads and a 0 otherwise. So, formally we'll just write that out. So, X equals indicator, coin, flip is heads. That's the indicator function. So 1 if the flip is heads, 0 otherwise. Let's flip some coins. So, I have some coins right here. They're actually euros. I'll just kind of show you the randomness here. So I have some coins here. I have a euro. I have a heads here. This would be a tails. So I just flip it and I'll just tell you what is X. So I got a tails. So X is a 0. Flip it again. I get a heads. So X is a 1. I get a heads. So X is a 1. I get a tails. So X is a 0. And I get a tails. So X is a 0. So all in all, right, I flipped the coin 5 times. I got 3 tails, 2 heads. So I got 3 zeros and 2 1s for X. So X here is a random variable. Every time I flip the coin, I'm randomly going to get a 1 or a 0. It's randomness to it. So I think that's maybe something that people don't necessarily understand. Think about it from a simple perspective or from a dice roll. These are random things as long as you flip it right. You don't do this where you just like toss it up in the air. As long as you actually flip the coin, every coin flip gives you a random heads or tails. So what is P of X is 1? That's the probability that a coin flip is heads here. So if a coin flip is fair, then the probability of a heads, or probability of X equals 1 equals 0.5, which is also the probability of X equals 0. So if a coin is fair, the probability of heads is equal to a probability of tails. How can we estimate P of X equals 1? Down here, we can flip a bunch of coins and we can calculate the proportion of heads. So in that case right there, I just flipped 5 coins. I got 2 heads out of 5. So I might estimate that the probability of getting heads is 40%. Now, if I keep flipping coins and my coin is fair, I should get closer and closer to 50% if I just do that. So that's taking a sample, right? This is a coin. If this coin is fair, I know this coin is fair. It's a euro. It's not weighted coin. I know this coin is fair. So I know the probability is 0.5. But if I want to estimate that probability, if I didn't know that, I'd flip a bunch of coins, determine the proportion of times I got heads, and that would be my estimate for the probability of getting a heads here. In this case, a coin flip is called a Bernoulli random variable. Bernoulli random variables. So a random variable X is Bernoulli pi if X takes the value 1 with probability pi, and X takes the value 0 with probability 1 minus pi. Bernoulli random variables are binary, which means they take 2 values. So, you might be familiar with coding language, binary code, that kind of stuff. This goes to that. It can only take 2 values, 1 or a 0. The expected value of a Bernoulli random variable is pi. And if we flip millions of coins, the proportion of heads should be about pi. So, if I keep flipping this thing over and over again, keep flipping it over and over and over again, and I count the percentage of heads, it should get close to about 50%. And just to be clear, so probabilities, right, are expressed between 0 and 1. But if you multiply 100, you'll get a percentage. So don't be afraid of a 0.5 probability. It's just a 50% chance. So here's another example, a Bernoulli example. Consider a dice roll. So a dice roll, right, can take on the value 1, 2, 3, 4, 5, or 6. If our variable is x equal the indicator function that the roll is 6, that's Bernoulli. Why? Because the dice is either going to roll a 6 or it's not going to roll a 6. So if the dice is fair, then x is Bernoulli with probability 1/6, right? Because if the dice is fair, every value is equally likely. We'd expect about 10 sixes, 60 over 6, in 60 dice rolls, assuming the coin is fair, or dice is fair. Okay, independence plus gambler's fallacy here. You might hear in a casino, if you've been to a casino, if you're old enough, I'm on a hot streak, I can't lose. Or you also might hear, I lost 5 times in a row, I can't lose the next time, I'm all in. But both of these games, both of these assume that the games played in the casino know about the other games. This is called gambler's fallacy. In the example of coins, the coin here doesn't know that I just flipped 2 heads and 3 tails. So it doesn't know that it should be, more like a heads on the next time. It doesn't know that. It doesn't know that information at all. Just like in the casino, if you play roulette and you roll a red, the roulette game, like the luck and the randomness of the game, doesn't know that you rolled a red before. So they're called, this is called independence. These events are independent of previous events. So for example, independence, does the birth gender of a parent's second child depend on the first? It's a question, yes or no. And the answer appears to be no. Does the score of the Saints game depend on what you ate for breakfast? The answer is no. So I think there's a lot of people that are superstitious about sports and things like that. Oh, when I sit on my couch on this spot, the Saints do better. It doesn't know about those events. Does the price in tea in China affect whether there's heavy traffic tomorrow in New Orleans? No, it doesn't. Each of these examples contain independent events. So each of these events are independent of each other. So the score of the Saints game does not depend on where you sit on your couch or what you ate for breakfast. Probability and independence. So this is going to get a little bit mathy. I'm not as concerned that you really know all of this. I'm just going to kind of walk through these kind of fundamental characteristics and probability that we need here on. So do not be afraid by this. And I think you've probably seen some of this in your last class. So 2 random variables, X and Y, are independent, which could be, a first coin flip could be X, a second coin flip could be Y. In this case, they would be independent, right? X and Y. X is the first coin flip. It's either a 1 or a 0. Y is the second coin flip. It's either a 1 or a 0. Those events are independent. It doesn't know. But the formal mathematical definition is the probability of observing any value for X. So X here could be a 0, little x, 0, 1, and little y could also be 0, 1. If this probability is equal to the probability of X equals little x and X equals little y. So for example, in the coin flip, right? If I flip 2 coins, I have X and Y. X equals 1 if first flip heads. Say Y equals 1 if second flip heads. So in this case, right, X comma Y could equal 4 things. Could equal 0, 0. That means both tails. Could equal 1, 0. That means heads, tails. Could equal 0, 1, which is tails, heads. And it could equal 1, 1, which is heads, heads. And all of these events take place equally likely. So the probability of each, prob of each, is 1 over 4, because there's 4 different options here. Now, I can also get this probability by multiplying the probability of each event. So in this case, right, this one right here, the probability of getting both tails is 1/4, right? but I can also get this equal to the probability that x equals 0 times p of y equals 0, which is equal to 1/2 times 1/2, which is equal to 1/4. So in this case, the coin flips are independent. Okay, here's some examples. Consider the birth gender on children. So these are the birth certificate values. So consider a mother that wants to have 2 children with the assumptions that both birth genders are equally likely. So again, does not have anything to do with gender identity, just based on when they're born. So maybe later they decide, feel like they're a different gender or whatever. This is just birth gender for this example. So you could have a boy girl or girl boy. You could have girl girl or boy boy. Each of these would happen with probability 1/4, and I'm not considering intersex here. So you could have 2 boys with probability 1/4. You could have 2 girls with probability 1/4. You could have 1 boy and 1 girl with probability 1/2. Why is that 1/2? Because the first kid could be a boy, the second kid could be a girl, or likewise, the first kid could be a girl, second kid could be a boy. The probability of 2 girls here is the probability of the first kid is a girl times the probability of second kid is a girl, which is 0.5 times 0.5, which is 1/4. So they end up working out. So they're independent events. Probability of 1 boy, you can also calculate, right? That's his here. It's the probability that kid 1 is a girl, kid 2 is a boy, kid 1 is a boy, and kid 2 is a girl. So that those are the options, right? So 0.5 times 0.5 plus 0.5 times 0.5, that's 1/2. Consider 2 coin flips or multiple coin flips, right? So let xi denote the result of the ith coin. x1 equals 1 and x2 equals 0. That means the first flip was the heads and the second one was tails. If y is equal to x1 plus x2, that is the number of coin flips in the first 2 heads, right? So y could equal 0, or number of heads in the first 2 coin flips. Y could equal 0, y could equal 1, y could equal 2. So y here is a binomial random variable. 2 is the number of flips, and pi is the probability of observing a success here. So here, y equals 0 with probability 1 minus pi times 1 minus pi, which is 1 minus pi squared. Y equals 1 with this probability here, 2 times pi times 1 minus pi. This 2 is because, right, y can equal 1 if the first coin flip is the heads or the second coin flip is the heads. So you have 2 different ways to do that. And y equals 1 with probability pi squared. So here's some summands here. Consider n independent Bernoulli random variables, x1 to xn. So they're all independent. That means the coin flip that I flip on the next flip doesn't depend on the previous ones. Then y, if y is the sum of all the xi's, all these Bernoulli random variables, then this is a binomial random variable with probability pi and n observations. So I can write this distribution like this here, down here. So this is a probabilistic model. It's something we can assume about our data before we actually collect it. So before I actually flip, 5 coins and measure how many heads I have, I might assume that in 5 flips, I have a binomial distribution. Which means I'm assuming that each flip is independent. So here's how you just fill this in. See this probability distribution up here? If you want to look at the different probabilities, all you do is feed in the different values of y. So you feed in y equals 0, y equals 1, y equals 2, all the way up to y equals n. So in the example we saw, we just plug in 0 here for y, 2 for n. We end up getting this probability. For y equals 1, we end up getting this probability. And for y equals 2, we end up getting this probability. It matches what we had on the previous slide. So how do we do binomial random variables in R? So obviously, I can sit here all day and flip a bunch of coins, but it might take me a long time. Instead, what I can do is I can use R to actually do a lot of coin flips for me. and see what that looks like. So here's the help menu for R binom here, or D binom. R binom is a function that gives you random numbers. N is the number of times to generate randomly. So size here is N on the previous slide, and N is the number of observations here. And you can see that here in the arguments. Down the arguments, N is the number of observations, size is the number of trials, so the number of flips, and probability is that pi. So I can run it. Here I have this R binom function. You know, I can randomly generate one random binomial with size 2 and probability 0.5, I get 2. So that means 2 heads out of 2 flips. I can get a 1, so that means 1 heads out of 1 flip. I can also get another one. This would be another random variable here as well. I get one flip here. D binom here, this gives those probabilities. So this is saying, hey, what is the probability of observing 0, y equals 0, given 2 flips and a probability of 0.5 of success? And that gives me 0.25. This is, hey, what's the probability of 1 heads out of 2, given 2 flips and a probability of 0.5? It's 0.5. This is saying, hey, what's the probability of 2 heads out of 2 flips with probability 0.5? It's 0.25. I can also generate lots of random variables together. So this up here, D binom, this is calculating these probabilities right here. This is just this function here. You plug in y is your initial value. You can see that here. D binom, you plug in an x, which is your y value. You plug in your size, which is your n, and you plug in a prob, which is your probability. So all it's doing is it's taking this function up here and it's plugging in your n, plugging in your y, and it's plugging in your pi and giving you a number. So the numbers I get here is for y equals 0, n equals 2, and pi equals 0.5. I get 0.25. When I change y to 1, I get 0.5. And when I change y to 2, I get 0.25. Now I can also generate a whole lot of random variables, binomial random variables. All I need to do is change this first number, which is 1, which is how many do I want to generate, to a larger number. So maybe I change it to 20 here. So here, these are 20 different sets of this experiment. The first time I got 0 flips out of 2. The second time I got 2 flips out of 2. The third one I got 1 flip out of 2. The fourth time I got 0 flips out of 2, et cetera, et cetera, et cetera. So altogether, these are 20 different times where literally what I did is I flipped this coin. 1, 2 times, and I got 1 tails, 1 heads. So my y is 1. Okay. This is randomly doing that for me. So I don't actually have to flip this coin anymore. So I don't need it. I can use this table function to get an idea of how many times each outcome happened. So here I have my x value here. This is my vector. And if I plug in table of x, so I plug in my function into, or plug in my sample. So x I've defined here, it's actually going to pop up in R. And if I plug it into the table function, I get a 0 5 times. That's how you read this. A 1 10 times, and a 2 5 times. And so I can count those, right? Sorry. I get 0 1 2 3 4 5 times. And I see that there. Okay, what if I flip 1,000? If I do this 1,000 times, if I do this 1,000 times, I can do this with table R binom 1,000. I'm doing it 1,000 times. I've got 2 flips each time and a probability of success 0.5. I get 247 zeros, 519 ones, 234 twos, which are close, right, to these true probabilities. So again, right, random samples, we don't actually know the truth. We're just trying to estimate it based on taking random samples. In this case, right, we make an assumption about where our data comes from. If we have a coin, we know it's fair. I can also use the hist function. So hist here can plot it. So I can say hist, you know, of our binom, and it'll show me, hey, look, this is the number of times I saw a 0, number of times I saw a 1, number of times I saw a 2. My binomial expected value is n times pi. Now, what is that? That is basically saying, hey, look, if I flip 2 coins how many heads do I expect to get? And it's the number of coins times the probability of getting a heads. So in a fair coin place, right, I have, in this case, 2 coins with a probability of heads of 0.5. I expect to get about 1 heads each time that I run. So it's random still, right? But that's what I expect. And you can see that as you get more and more observations, you sample more. So here's 10 times I do this experiment. Here's 10,000. As I get more and more and more, I should get closer to this true value. I can plot these binomial probabilities using this code at the top. So this is the first introduction of plot here. So what this does is gives you a sequence 0 to 10. And I'll walk through this again once I get into R later on. And then I'm plugging in this sequence. So it goes 0 to 10. What this means, just to show you. In R, this shorthand, this shorthand makes a vector that looks like this: 0, 1, 2, 3, 4, 6, 7. That's what this vector looks like. And I'm plugging in here. So this is my X argument in the plotting command. So you see on the left, plot XY. You put your X axis here, then you put your Y value. So it makes like a scatter type plot. And then type here gives you a bunch of different options. You can use points. You can do H, will make vertical bars like here. The other arguments in this function, you have main, which is what is your title. You have xlab, which is what is your X label. And we have ylab, which is what is your Y label. So you can see up here, just on the bare minimum, and maybe I should kind of go into R for this. Let me get out of this here. So if I go to R, just kind of open a new one. So if I do plot, 0 to 10, 0 to 10, this is just going to plot data points all together. You can see they're all kind of increasing, pops up in my plot window down at the bottom. If I want to add a title to this plot, I might say main equals first plot, like that. Now you can see it added this here, first plot. This is just a scatter plot, right? I can change my Y label. So I can say Y label like this, or Y axis. Now you can see this right here. I've got Y axis. I can adjust my X label using the same kind of thing. Say xlab equals X axis. Have that there. And then I can adjust kind of how this looks with type. So type here, type equals L will produce a line. See a straight line. Type equals O will produce a straight line with points. Like this. Type equals P will just produce the points again. And type equals H will produce these horizontal bars that you see. So the only difference here is I'm plugging in these D binomes here. So I have, D binom 0 to 10, and I think I had 10 and 0.5. You can see these probabilities here down at the bottom. See how it does it for each item, 0 to 10, does the whole sequence. And then I can plop this in right here. So this is what it looks like. So this produces like the same kind of plot as you see on the lecture slides. I can also change this too here. All this is doing here is I'm going to change the type to O here instead. So O is basically going to, and ignore this right here, this part, sorry. O here is going to connect the dots. Right, so you can see that over here. I have this plot in R, and I can change this to type equals O, and it will connect the dots. You can see that. Some basic plotting as well. I can generate Bernoulli variables using the R binome with size equals 1. So 1 observation here. So, if I want to flip a coin, I could say R binome 1, 1.5. Oh, I got a 0. Oh, I got a 1. Oh, I got a 1 again. So I got a heads, zero, tails, a heads, tails. If I want to do 2 flips, right, I change this to 2. Okay, let me put inners. Okay, I got 1 heads, I got 2 heads, I got 1 head, 2 heads, 1 head, 0 heads, et cetera, et cetera. Other binomial binary random variables. How many COVID deaths are there in a given city? Or if you get COVID, are you going to be hospitalized or not? That's a binary random variable. So the number of hospitalizations per COVID case would be, given number of the COVID cases, how many were hospitalized? Another binary random variable could be tumor response. Did the tumor shrink after it got chemotherapy? Election results. Did candidate A win a given district? Or if we're talking about, the national presidential election, did president win a given state? Those are all binary random variables. Okay, normal random variable is another distribution here. And I'm not going to get into a lot of the distributions, but these are kind of the most important ones. And, if you go look at normal on Wiki, you've probably seen a plot like this, the bell curve, Z statistics. That's what that's referring to. So this is just the probability distribution. If you want to get a probability of getting any value, all you do for a given, maybe mu is 0, mean is 0, sigma is 1, which is the standard normal distribution. You just plug in all those values here and you get a number. And I'm not really crazy about using this. I just want to show you just another example. And again, this is not a big part of this class. The theory behind it, I just want you to have a little bit of understanding. That's why I'm doing it here. But afterwards, we're going to be mostly doing practical things. So normal random variable, what if I want to estimate this quantity? What's the probability of observing x equals 1 given mu equals 0 and sigma equals 1? Well, this is my PDF here. And all I need to do is for every sigma spot, I plug in a 1. So this goes away. Sigma spot, I plug in a 1. For every mu spot, I plug in a 0. And for every x spot, I plug in a 1. So if I just do the math, I get 0.252. You can see that here as well. But I can also get that from just doing d norm. So if I look at, help d norm, this is for normal distributions generating random variables. So d norm, the syntax is I plug in my x value, I plug in my mean, which is my mu, and I plug in my standard deviation. So I just plugged in d norm 1, x equals 1. That's this right here. 0, that's this. And 1, that's this. So this is the syntax here. D norm x mu sigma is equal to f of x mu sigma. So what do normal random variables look like? I showed you some on the page here. They're all symmetric, right? And they kind of vary around bell curve, right? You might have heard they all vary around this mean. So this is a normal 0, 1, the standard normal. This is normal 0, 4. It has a bigger range, you can see, right? This is a normal 1, 1. It's shifted to the right. This is a normal 1.1, so it's very small. I can also generate random normal variables using R norm in the same kind of way. So here I could say, hey, look, x here, I'm defining this x value is equal to R norm, 100, 0, 2, and then I'm going to print out x. And I can also make a histogram of this thing. I just want to show you that here. So if I clear this, everybody should be on the same page. So I've cleared this, right? So I don't have anything here. I could say x is 2. So now x is, I've defined, you can see it, it's 2. And I can actually run it in my console and it'll print it out. So all I'm going to do instead is I can say x is R norm of 10, 0, 1. And let me just show you what that looks like first, 10, 0, 1. 10 random variables from a standard normal. See, they're all different every time because it's random. So I can run this here, x, and then I can print it out. So these are my random values. And I can make a little histogram if I want. Hist x. This makes my little histogram. You can see that down at the bottom. Notice how if I want to zoom in, I click on this zoom right here. If you want to save images, to me, the best way to do it is to use the snipping tool. So I can use, the snipping tool and I can copy it and paste it somewhere else. Like for example here, bam, now I have my new histogram. To me, that's the easiest way to do it. So you want to download the snipping tool. And the last distribution that we really need to know for this class is the chi-square distribution. So chi-square distribution is the squared of the standard normal. It's like a normal distribution, but it's positive. Depends on something called degrees of freedom. So you have one value here. So this is a chi-square distribution with 1 degree of freedom. This is 4, this is 10 degrees of freedom, and this is 15. What you want to use these for, so just to give you an idea what's important. So these are the 3 distributions that are important, and I'll tell you what hypothesis tests assume. So for binomial distribution, this is used for 2 sample tests of proportions, 1 sample, logistic regression. For normal distribution, you might use this for z-tests, linear regression, and general linear GLM. So that would be, interpretation of logistic, for example. And then chi-squared are going to be important for chi-squared tests and categorical. And model building. So if this lecture flew over your head a little bit, I wouldn't worry about it. What I want you to get out of it is that there are random quantities, right? Coin flips, BMIs, heights of people in your neighborhood, whatever. There are random things that we're going to assume something about the structure of that randomness. Then we go collect data. And after we collect the data, that's what allows us to actually perform analyses. So that's it for today. Do not forget, right, I have homework I'll go through after next class. All right, bye everyone.